developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
My background is in energetic materials, in solid propellant, solid fuels, and in this project we're trying to integrate solid fuels into rotating detonation engines. In solid fuels, why we're interested in that is because they're much easier to store. They don't leak. So if there's a puncture in the device, you're not going to have a fire hazard with that. Potentially it could have higher energy density, but the challenge of bringing in a solid fuel into the RDE is how do we integrate it in, how do we go from a solid fuel to a gaseous fuel that the RDE can operate with. So that's a big focus of this project, is looking at fuels that can gasify on their own. So we don't have to bring in energy to turn that fuel into gas, but they burn, they propagate, and produce gas that can be fed into the rotating detonation engine.
So the goal of the research at Purdue University is to investigate the types of solid propellants that can be used in a rotating detonation engine, as well as the systems that would be required to incorporate those solid propellants effectively in an operating rotating detonation engine.
I've been focusing on a Raman spectroscopy experiment. We've gone through a few iterations of this. The idea is kind of to measure our propellant's gas composition after we burn it, because that gets fed into the RDE. So this most current iteration, kind of the new things that we're doing, is that we're actively heating all of our pressure vessels and our equipment. And that way we can test at more relevant conditions and get a more accurate idea of what our products are going to be. The other major thing different about it is that we're now calibrating for more species than we were before, which is very important to get kind of an accurate measurement of our concentrations in the gas mixture. So this is my Raman spectroscopy experiment. The idea here is to decompose our solid fuel in a closed bomb and then perform Raman spectroscopy on it in order to get an idea of the fuel composition and the various concentrations of all the different chemicals in there. Our solid fuel products flow from here. All the insulation has been removed. It's all heated and insulated to maintain relevant conditions. This windowed cell is where we do the Raman spectroscopy. Our laser comes in through here. We have a 532 burst mode frequency laser. Scattering occurs inside the cell and it gets collected over here by the spectrometer. We essentially can do analysis of that spectra to identify the different chemicals inside our gas mixture. And then using very careful calibration and post-processing analysis, we're able to essentially determine the relative concentrations of our mixture.
I'm working on the solid fuel RDE project, doing work with surrogate testing. So that's when we take a mixture of different gases, different amounts of those gases in a mixture, and test those with two different experiments that we have going right now. One of those is the detonation tube, which is just a long tube that we're filling with gases and then sending a wave in to detonate those gases to see how well those are reacting, as well as putting it through our RDE we have in the facility here, our rotating detonation engine. And we're varying the amounts of CO, nitrogen, hydrogen, and air to measure the operability of both the RDE and just the performance of the detonation wave under a bunch of different mixture conditions. So the main performance parameter we're identifying in these tests is wave speed. So it's one way we can film the aft end of an RDE, or we could film the det tube, is what we call it, from the side to see our detonation wave pass. And basically the faster the detonation wave is going, the better for our mixture. So that's going to yield a higher energy release per that mixture. And we're going to try to push our target mixture towards realistic conditions. So we're seeing what propellants are yielding what gas mixtures, and then we're trying to simulate those gas mixtures in our facilities to see if it would be possible to implement a solid fuel RDE eventually.
The gas generator has two purposes. One is to couple with the RDE, act as a standard solid rocket motor and feed our fuel into the RDE so we can detonate it. And then second, it's going to act as a closed bomb. So we're going to put some propellant in there, and then it acts as a mixing chamber where we can feed our detonation tube. The experiments from the detonation tube kind of go hand in hand with the surrogate testing in the RDE. So designing that entails lots of iterations in CAD, and then going through some stress analysis and finite element analysis. And then we're going to move to some hydrostatic testing once all of our parts are manufactured and the gas generator is assembled. And then we're going to validate it, make sure everything's looking good with some standard solid propellants like ammonium perchlorate, and then get some good measurements, pressure, temperature, make sure that nothing is misbehaving when we're ready to fire this thing.
The idea to use solid propellants for rotating detonation is a fairly new one. So some of the innovative work that's been done at Purdue and a couple other places in the US is really cutting edge technology. So we've demonstrated burning propellants and producing something that could then burn again in a rotating detonation engine. So that proof of concept is really key to being able to turn on additional funds to do a more substantive effort in maturing this technology for an actual application. It's a very high interest technology across Department of Defense. So it's a very important technology for the warfighter.